Okay, hello, can you hear me? Please, if you can hear me, let me know. Please, can you hear me?
Yes, I can hear you. Yes.
Okay, okay, yeah. So we are going through the unit two, and it's basically a question solving session. But when we get to the controls part, when we get to the controls part, I will take time to explain that part of it. Okay. So for this particular question over here, I was solved in class, and I think the solution is also in the slide. So, but if you have any question you think we should go over it again, we can do that. In the absence of that, we can skip this particular question because the solution is in the slide. Should we skip it? Yes. Okay. So we go
Yes.
straight to. Okay. So I heard someone said no. So this is a question. The question says we have a DC machine which is rated at 15 kilowatt and it's 92% efficient. Whenever you have a machine and you see its rating, its power rating, it means that is its output power. So the power you have over there is its rated output power, and you'll be given efficiency. So if you have output power and you have efficiency, then you can determine the input power because the machine is not 100% efficient. If you give it 15 kilowatts power at its input, it's going to give something less than 15 is going to give you something less than 15 kilowatts. So then you need to give it something more than 15 kilowatts so that the extra one will be wasted in the machine. Then at the end of the day, you get a 15 kilowatt as your output. Okay. Then for this 15 kilowatt machine, which is 92% efficient, it's rated amateur voltage. This is the maximum voltage you can apply to the amateur, and it is 400 volts. And when you apply this 400 volts to the machine terminal or the armature, it's going to generate a back EMF. And this back EMF is going to give you 1500 RPM. Okay. Then we are asked to determine the resistance of the motor armature, then its machine constant. So the windings in the armature windings are conducted, therefore they definitely have some level of what resistance. And if it produces speed, it has a certain what machine constant. So if it can produce speed, it can produce torque. It has a machine constant, and this machine constant. Okay, so let's go to what's going on. Okay, let's go to Jamboard. Okay, so over here we are supposed to determine the resistance. Then we are also supposed to determine what the machine constant. We know that the back EMF. So basically, let me explain how uh, the motors work. So we know a motor gets an input. Okay, the motor has a resistance. Okay, we are looking at okay. So let's say this is a machine's load, right? Or this is a machine, this is an armature, or whatever load is coupled to it. Then you have a certain supply. Okay, so let's call it VA. This is the voltage applied to the armature. Okay, then this here is going to generate what a certain back EMF, and you have a resistance here. Okay, so then this EMF here is the back EMF, and we said that since this is the supply, this before the machine starts, this has a higher potential than, or the potential here is higher than the potential here. So you have VA equal to if a certain current IA flows, and it is this current that produces what the torque. So if IA flows, then you are going to have what IA RA plus what EB according to Kirchhoff's voltage law. Okay. Then if at the starting of the machine, when the machine at the starting of the machine, or when you see that the machine is at standstill, because we know this EB is equal to Km omega R. Therefore, anytime you see a question that says a standstill or the machine is stationary, when a machine is stationary, it means what its rotor speed is what zero. So then your omega R is equal to zero. Then if your omega R is equal to zero, it means the EB is also equal to what zero. Then at that instance, you are going to have your VA equal to IA RA. Okay. Remember the armature of a motor is very small. Since this resistance is very small, a very high current is going to flow through the motor. So that's why if you start the motor, it draws a very high current. A very high current is going to uh, flow through this. I hope that makes sense. Then let's look at the instance when the motor starts moving. So if this motor starts moving, it means its speed has started or increasing. Then if its speed has started increasing, then it means what EB has started increasing. Then if EB is now increasing, then the potential difference between this and this point will be getting or smaller. And if the potential difference between two terminals are getting smaller, it means the current flowing between these two terminals will start reducing. Therefore, if the machine starts speeding, you see that your back EMF will start increasing. Without this back EMF, there will be no speed. Okay, then if the back EMF starts increasing, current will start reducing. Okay, and this will happen. So the motor will continue speeding. Motor will continue speeding. Okay, then this one will continue dropping until the point where EB becomes equal to where. So we are still looking at the motor at a standstill. We are looking at this from the point where it was standstill, where EB was equal to zero. So now it's no more standstill. It has started what accelerating. So its speed will keep increasing until EB becomes equal to what VA. Then if EB becomes equal to VA, it means the potential here and the potential here will now be their difference will be what zero. Therefore, your current will become zero. Okay. At this point, we've not the machine is what unloaded. Okay. So this machine which was unloaded, which initially was at standstill and now has reached the maximum speed. So then the maximum speed is going to occur when VA is equal to EB. Okay, that's when you are going to have the maximum speed. Okay. Then what happens when we start loading this unloaded machine which is at maximum speed? This is at maximum speed, and if assume you are running at a certain speed, then someone just pulls you back, the person will reduce your speed, right? So this running at maximum speed, the moment you couple a load to it, remember a load is a torque. The moment you couple a load to it, the speed starts or dropping. Okay, the speed will drop. And if the speed drops, then it means EB has dropped. Then if EB has dropped, it means that now EB is less than what VA. I hope it's making sense. So it means EB is now what? Less than VA. So if EB is now less than VA, then current will start flowing again. Okay. And the amount of current, then as we continue adding more load to this machine, the back EMF will continue dropping. Then if it continues dropping, then the potential difference will continue increasing. And this current will continue increasing. Then if more current is dropping, we know that the electromagnetic torque produced is equal to the machine constant times the armature current. So if you add more load, which is more torque, more current is going to flow. The machine is going to generate more torque. Okay, because the torque applied to the machine or the load on the machine is high. I hope that explains how the motors work. Now, if it happens that this armature here or the rotor here is being driven by a prime mover, okay, if this armature over here is driven by a prime mover at a very high speed, then it's possible that you because as the speed increases, EB is increasing. So then it will get to a point where the EB becomes greater than VA. If EB becomes greater than VA, then now the potential here is going to be higher than the potential here. then current will start flowing this way from the motor to what? The source. Then we said that the motor is now what? Generating. Okay, I hope you get the difference now. Okay, that's just by the way. Let's solve the question we want to solve. Okay, so this machine has a P out, or its rated output is what? 15 kilowatts. Its efficiency is 0.92. Then 8 V rated. So that is V in rated, okay, or VA rated. That's the rated armature voltage. Okay, this is equal to 400 volts. Um, okay, I think that's all the parameters that were given. Okay, we know this machinery, the motor equation that VA equal to IA RA plus what? EB plus LA DI DT. Okay, but if we are doing analysis in steady state, it means there's no change in armature current. The armature current is now what? Constant. Then the change here will go to zero. So the whole of this part will go to what? Zero. Then our equation reduces to what? VA equal to IA RA plus what? EB. Okay, we learned that the uh, power is equal to what? The torque times or the angular speed. Okay, torque times angular speed will give you power. And this is mechanical power. This mechanical power is also equal to the back EMF that the motor generates times what? The armature current. We have this. So there are a number of ways you could solve this question. So then one way is, okay, if I decide that I want to multiply this through by what? If I want to multiply through by IA, then I'm going to get IA VA. Then I'll get what? IA squared. Then I'll get what? This. This one here is the output mechanical power produced, which is what? The 15 kilowatts. This is the drop, or this is the losses. This is what makes it 92% efficient, or this what doesn't make this motor what? 100% efficient. Then this is your input power. Okay. So first of all, we have the efficiency, and we know efficiency is equal to what? Output over input. So this is going to give us what? 15 kilowatts divided by what? A certain power. Let's call it P in. So then P in should be equal to 15 divided by 0.92. And this will give us what? I think 16 point something. Okay, 16.3 kilowatts basically. Okay, so now I know that IA VA, which is the input power over here, the input power to the motor should be equal to 16.3 K. Then I know VA, which is 400. So then IA is equal to 16.3 times 10 to the power 3 divided by 400. Okay, that's going to give me the rated um, current, or yeah, the maximum current that will flow through this. And that is what? That current is 40.8 amps. Okay, I hope you are following. Hello, are you guys there?
Yeah, we have to.
Okay, so now that I have this current, over here. I know the machine is 92% efficient. That means it is 8% inefficient. Is that okay? So that 8% inefficiency is as a result of what? The I squared R losses. So then I know that this over here, which is the IA squared RA, should be equal to what? 0.8, 0.08% of what? The input. And I know the input to be what? 16.3. K. Okay. And I know IA. So then R should be equal to 0.08 times 16 times 16.3, sorry, times 10 to the power 3, all divided by what? 40.8 squared. That will give me what? RA. I hope that makes sense. So that will give you the value of RA. Okay. Now we've been given the rated speed. Now we know that. Oh, I don't want to go to the next page. We've been given the rated speed to be what, 1500 RPM. Okay. Then we can find the EB that corresponds to this 500 RPM. So that's when you have 400 applied to what, the armature. So if you apply 400 volts to the armature, it's going to produce a certain EB. Okay. So we know that this EB times IA, that will be our output mechanical power. And that in this case is equal to what, 15K. So then I can say that EB should be equal to, so you can use the torque to find Km, you can use this the speed to find Km. Let's look at the two um okay, sure, let's go. So we have EBIA equal to 15K. Then EB should be equal to 15 times 10 to the power of 3, all divided by what, 40 point, I think, 83 or whatever it is. Okay, then this is going to give you what, EB. And EB is equal to what? So this EB will give you 368 volts. Okay, then we know this EB is equal to Km times omega R. Okay, then if I want Km should be equal to EB divided by what? Omega R. But this formula here, if you want, if you just go ahead with this 1500, it's going to give you, because this is in volts and this is one. If you go with this is in RPM. This is in RPM, so you are going to get what, volts per RPM. If you want it in volts per radians, then you have to convert this speed over here into what, radians. And if you convert this 1500 RPM to radians, that's going to give 157.08 what, rad per second. Okay, so then this should be equal to 368, right? Divided by volts divided by 157.08. Okay, and if you do this, this should give you 2 point something. Okay, so this will give you 2 point something. I think 2.34 volts per what, rad per second. Or sometimes you see it written as 2.34 volts second per rad. Okay, it's because this S comes to multiply this. Okay, who is not okay with the solution we have right now? Okay, if you're not okay or you don't understand the solution we've had right now, you can voice it out or you can put it in the chat. Okay, sure. Now let's go on. Mm, okay, so we have choppers. I'm sure you've read through choppers already, so let's go straight to the questions. But when you get to the controls part, I may take time to explain that. These two quadrant choppers. Okay, these two choppers. Okay, so let's look at the example on chopper fed DC drive. So you have a DC motor which has rated values of 230 volts, 500 RPM, 90 amps, a resistance of 0.115 ohms, and an inductance of 0.011 Henry. So this DC motor is fed with what, a two quadrant choppers. The question is, what are the choppers doing over here? The choppers are just what, power electronic devices. So the issue is we have a DC source and a DC source which is constant, but we want to vary the speed in our motor. Okay, and we know that if we want to vary the speed, it depends on what, the voltage. So that if we can vary our voltage, we can vary the speed. But if you have a DC source, the value is fixed. You can't do anything about it. Okay, if you want half speed, just like the man said yesterday, you can't take your calculator and half the speed and expect to have half speed in your motor. Okay, it has to go through a certain form of transformation. But we have a DC motor and we have a DC source. So then we don't need a rectifier in this case. We just need what, a DC to DC converter, either a boost or a back boost, whatever it is. It depends on if you want to increase the speed, then you change something. So what we are doing is we want to control someone, but we can't control the person directly because we don't have power over that person, or the person is not within our jurisdiction. Okay. So then we find someone who is within that jurisdiction who can also influence that. Someone we have influence on. So right now we want to vary speed, but we can't vary our voltage source. So we look for someone we can what, influence. So we take the power converter. We know the power converter can take that input which we don't have, we can't change, like we can't change us, we just take it and change it. Okay. We take that DC, then we are able to control a certain parameter within the power electronics. Then by controlling that parameter, the power electronics is going to give us what, a different voltage from what we are supplying to what, the power converter. Then we feed that output of the power converter to the motor, so that we just be changing a certain parameter within the power converter. And for DC, for the choppers, what we change is what, we change the duty cycle. Then for the rectifiers, we change what, the firing angle. I hope that makes sense. Okay, so now our power converter here is a two quadrant chopper. When we say two quadrant, it means that this chopper is capable of what, giving you, or it will help you to what, reverse. It can help you to reverse or torque, but you can't reverse for speed because it's just two quadrants. I hope that makes sense. If you want to reverse speed, you reverse what, voltage. If you want to reverse torque, you reverse current. So these two quadrant chopper can help us what, to reverse the current, as we will see in the second part of this question. Okay, so that's a two quadrant chopper. Okay, so this two quadrant chopper uses a supply voltage of 230 volts. So this is the input. This is not the 230 over here is not the input to the 230 you have here over here. This is the input to the power converter. Okay, and this is the rated input to the motor. This is the maximum one you can supply to the motor. But this power converter here's input voltage is of 230, and it has a switching frequency of 400 hertz. If you read the materials, you see that in our application we are only varying what, the on time, okay, or the duty cycle, but we are not changing the switching frequency and we are not changing the switching period. We are just changing what, the switching time, the duration within the entire period where we have our switch was conducting. Okay, that's what we mean by changing the duty cycle. So this is a switching frequency, and this will give you, if you find the inverse of this will give you the switching period. And we are supposed to calculate the speed for motoring. Okay, so because you see the motoring over here, it tells you that what, current is what, the current is positive. Okay, because we are looking at motor. So any when the current flows from the source to the the motor, we call it what, the positive. Okay. So we are to calculate the speed for motoring at half rated or torque. The current you have here is the current that will give you what the full or the rated torque. We are supposed to find motoring at half torque. Half torque means what? Half current. Okay. And we are using a duty cycle of what? 0.5. Okay. I wish I can copy the question and paste it in on Jamboard. Okay. So let's go to Jamboard. Okay. Yeah, so we have our IA rated to be 90 amps. We have our VA rated to be 230. Please don't confuse this with the input to the power converter. We have RA to be 0.115 ohms. Okay, I didn't bring volts here. You all know the units for voltage. So, yeah, you have the inductance to be 0.011 henries. Okay, sure. Your duty cycle is equal to zero point 0.5, and your your supply, so your V supply is also 230 volts. Okay, so we are looking at a motor, then we can write what VA is equal to IA RA plus what EB plus LA DIA DT. Okay, we are looking at analysis in our steady state. Okay, so this is equal to 0. Someone is asking if this is supposed to be equal to 0, why were we giving LA? Go and use it. Okay, the fact that you are giving this doesn't mean you always have to use it. Okay, look at the kind of analysis you are doing. If you are doing transient analysis, then this place, you can't ignore this place. But if you are doing steady state analysis, most of the time, if you are doing the analysis for the motors, we are going to be doing it in steady state. But maybe we'll be solving a question where we are looking at switching analysis. In the switching analysis, that's a transient analysis. Okay, that one we are not going to ignore this. So in for now, we are doing steady state analysis. So this one goes to zeros. Then I have my VA to be equal to what IA RA plus EB. Okay, that's that's all. But what is VA? For a two quadrant chopper, we know the average armature voltage is equal to what? The duty cycle times what? The supply voltage to the power converter or the VDC, what is in the slice as was VDC. Okay, so then our VA in this case is going to be a 0.5 times what? 230. Okay, and this is going to give you what? 115. Yeah, 115 volts. Okay, so then we know VA. We want to find EB because once we know EB, if we know EB, we can find. Sorry, how many did you find? How many? If we have if we have EB, we can find speed. So then EB should be equal to our VA, which is 115 minus. Uh, we are looking at current at what? Half rated torque. So half of 90, that's going to give us 45, and we are going to multiply that by what our resistance, which is 0.115, I think. Okay, yeah. Okay, so this is going to give us a certain back. Okay, this is going to give us a certain back EMF. Okay, so this will give us an EB of um 109.83. Please punch it on your calculator as well. Okay. Okay, so now we have EB. But we know EB is equal to Km omega R. And we are looking for speed. We know this, but we don't know this constant. Okay. And remember, and remember, the machine constant is constant as long as the flux in the air gap is what constant, because this Km is equal to K phi F. Okay. So the question hasn't told us that the supply to the stator voltage has changed. So if the stator voltage has changed, then the field current has not changed. If the field current has not changed, then the flux has not changed. So then Km is Km. Km is constant in this case. Okay. So right now we don't know Km. So we need to go and look for Km. So let's go and look for Km and come back. Okay. Now we know the speed as what rated. We know the speed as what rated conditions. This rated condition, please pay attention here. This rated condition is when 230 is applied to, so the speed we have, which is 1200 in the question, that is the speed at which the motor is going to run. If you supply 230 directly towards this motor, okay, so if 230 is getting directly to the motor, then EB will be equal to what? So when 230 is supplied directly to the motor armature and 90 amps is flowing, we are going to have what? It to be what? We are going to have EB to be 230, okay, minus 90 times 90 to 0.115. Okay, so what to be EB? EB is to give us 219.5 volts. Then if this is the case, so the speed that corresponds to this back EMF, you know that speed is 1200, is it 1200 or 500? Okay, sorry, it's 500 RPM. Sorry, it's not 1200. I think there's a question that has 1000. Okay, so that speed is what 500. Sorry. Okay, then if the case, then Km should be equal to EB divided by omega R. Then Km should be equal to Km should be equal to 219.65 divided by 500 RP. Mindful of the unit over here, so this volt. Okay, so this the Km in this case is going to be 219.65 divided by 500 RPM. So that was 0.390 volts per RPM. Please be careful. If you can't yourself, convert this to what? Radians per seconds. Okay. I'm trying to trust yourself right now. Okay. So then we don't know Km. So then our speed omega R is going to be what? 109.83 divided by 0.4393. Okay. Volts per RPM. This is volt. If you are leaving your units in RPM, this when you are writing the equations, write the units so that it will remind you of what you are doing. Okay. So if we do this division, what are we getting? 109.83 divided by 0.433 volts per RPM. So volts will become volts. So then per RPM, 1 over RPM will give you what? RPM. So then this will give us 250 RPM. Okay. If you had converted this 500 RPM to rad per second, then this speed you get here would have been rad per second. Then you have to multiply it by pi divided by c. And I know you know how the two parts came about. Okay. So that's the answer for the first part of the question. The second part of the question says if if this motor now generating Okay, let me show you the question. So this machine is now generating with a duty cycle of 0.5 and at rated torque over here. What's going to the speed? Okay, let's go back. So then our EB will be equal to what? So 230 times 0.5. Okay, minus, so this is VA, right? Minus IARA. Minus, now because we are generating, it means EB is now what? Greater than V. Okay, remember the diagram drew at the beginning. So now current is going to go from what? EB to what? IA. Okay, so in that case, I think I do something like this. This is a motor. You have the back EMF. You have the. Okay, so when it's motoring, current is flowing this. Now current has reversed. So now current is flowing from what? The motor into what? The source. So if that's the case, then conventional positive current because it's a motor. Now this is going to be what? Negative current because it's now in the direction opposite to what? Positive current direction. So now we are still what? This is at what? Rated current, then times our resistance, which is 0.115. Okay. So then EB in this case is going to give you. So now that's plus. So you have negative. This becomes so you see that EB is now greater than what? VA. Because VA is still going to be I think, 150. And you see that EB would be 125 volts. I hope that makes sense. Okay, we've already found our machine constant, which is 0.4393 volts per watt RM. Okay, so then our speed in this case is going to 125.35 divided by 0.4393 volts per RPM. Please remind yourself always. Okay. And this was 285 RPM. Any question on this thing? Any concern? No.
There are questions in there.
Okay.
Emmanuel,
Yeah, please. If you have a question, unmute yourself and okay, raise your hand so that we can have some. We don't have two people unmuting and talking at the time. So okay, so if you have a question, you can just use the raise hand uh, there and
For I don't know. Like from when it was the starting to the
if you are finding difficult speaking to you, can type in the chat.
mm,
So please, if the text is not good, please use it.
okay, then let them.
Okay, so in the next 2 minutes, I'm waiting for questions. Please use that. It looks like your net is very bad.
Emmanuel, there are questions in the messages. Go and check it, please.
Okay, we are checking. So relax. There's no question in that. So if you think you sent a question to that, please resend. Okay, in the next minute.
please, I
Okay,
sent a question in the chat. I wanted you to clarify the VDC and the VE. The voltage supplied to the converter.
yeah. So the question is that this one it just happens that your input or the rated voltage for matcha is equal to your supply. So then the question is, why don't we just connect this directly? So if we connect directly this 230 to the machine, the supply and the machine maximum voltage, why don't we connect directly? If we do that, we can do that. But if we do that, it means no control. We can't change the speed more. The speed always have kind of the speed will always constant, and maybe that would depend on our loading, right? So that means the speed will always be constant. So there is a difference between the machine rated voltage is different from what the supply. So let me draw. So you have your supply over here. Okay, you have your supply over here. Then you have a converter in the middle here, and you have your motor here. So the output of this power converter is what supply is connected to the motor. Then this is the supply. Yeah, our supply is for DC. So it's a constant supply. So you connect that port there, connect this to this. Okay. And we are saying that what you feed in this question, you feed to the power, what you feed to the power converter. Okay, what you feed to the power converter is your supply, and in this case is 230. But what the power converter gives to the motor is variable. Okay, it's variable. So this place is the VA. Okay, VA is what goes to the motor. What or that's the output of the power converter. It is what goes to the motor. And because we want to vary the speed in this motor, we vary the voltage here, VA. Okay. And how do you vary uh, this VA over here, the output of the power converter? If this source is what constant, so there is a parameter for the parameter in the power converter as a duty cycle, and this cycle and VA have a relation. So there's a relation between the duty cycle, the supply, the power converter, and the output of the converter, and that relation is what the output of the power converter equal to the duty cycle times the that is entering it, which is what our VDC in case or our V supply. Okay, so that's with a constant VDC, and I'll be changing. If I'm changing this, I'll be changing this, and once I'm changing this, I'll be changing what B, and if I'm changing B, I'll be changing what omega R. This is your question answer.
Yes, please. Thank
Okay.
you.
Yeah. So some asks, how do we know? Uh, how do we are in steady state? Okay. So if if you are using the motor, if you are looking at the speed of the motor, the torque in the motor, we are looking at the transient. Okay, what's the long term speed or yeah, the long term for the torque is going to generate over a long period of time. Okay, so the LA, the IT is when like let's assume the motor is stationary, the motor is or everything, and you just energize. Okay, you apply the bit. Okay, for a very few seconds. Okay, because the motor is inductive in nature, so this this inductance in the motor will not cause current to just move from zero to the rated current like within C equal to zero within zero time. It's going to take time, okay, because with that an inductor doesn't allow it to change within this or um that's how the current needs to change instantaneously. It's going to take time. Okay. So the current to be right gradually. So if you remember power electronics, you see that current in the inductor will rise this way. Okay. It doesn't rise this way. It rises this way. Okay. Then when it's into it falls this way. Okay. That's what introduces or some form it it even allows you to kind of reduce ripple in current but not in voltage. Okay, so it allows the current you need to change gradually. It allows it to what change go down gradually. So when we are doing we are finding maybe the speed, the torque, and this one. We have to do the analysis in steady state. Okay, some of the questions will tell you that say the assumptions you make. No, you just have to. Okay, for most of these questions, you use the set, except you are doing for switching analysis. I think there's a question down there that we are going to do, and you see when we are using the LADIDT. Okay, yep. When looking at switching analysis, maybe when a certain switch conduct and when a diode is conduct, with that one, you are just doing some transient analysis or the switching analysis. So that one, the ADIDT play a role in that. Okay. So there are some further questions down there. Let's go and answer that. Okay, so we are done with this one. Okay, so there's some further examples on chopper fed right. Okay, the first one. It says a single quadrant chopper feeds a DC. Okay, let me do it this time because I have to be making reference to something. Okay, it says a single quadrant chopper feeds a DC machine which has the following parameters. The resistance is 0.2 ohms. The industry is 10 milliamperes. The machine constant is 2 volts seconds per rad. It's the same as volts per rad per second. The chopper supply voltage is what? The chopper supply. So remember, that's the supply what? The chopper. So the chopper supply voltage is 400 volts. At particular operating point, the speed is 100 revolutions per minute. And the mechanical output is what? So at a certain operating point, speed is 100 revolutions per minute. So at a certain point, the speed of the motor is what? 100 revolutions per minute. And the mechanical output of that motor is 8.4 kilos. The peak to peak current ripple at this operating point is what? 10 amps. You have to determine what the chopper cycle. Okay, determine the chopper duty cycle, then the estimate switching frequency. That's the approximate switching frequency. So when we get there, we talk about that. Hearing what the effect of what the resistance. So that if you are doing the analysis, IARA will be what zero. Then you are reduced. Okay, the power loss. Then you are supposed to determine power loss in the resistance, assuming the resistance is constant, regardless of what 50 and mixed interval simplification actions and the amateur current waveform. Okay, so one assumption you make here is that you are operating in what? Continuous current. Because if current is not continuous, if you read the materials, you know that we can use VA equal to delta VD. Okay, because okay, I don't want to go through the entire materials, but I'll try as much as possible to explain things to you. So you need to make the assumption that you are assuming the current is what continuous. If the current is continuous, then the average amateur voltage should be equal to what? Um, should be equal to the DC cycle times for the VDC. Okay, so let's go back to okay. So let's go to the next page. Okay, yeah. So we know our VDC is equal to 400 volts. right? Um, we know RA to be, okay, we open that. We know KM to be, I think, 2. Okay, so RA is 0.2 ohms. KM is 2 volts, 2 volt seconds per watt, right? Um, LA is equal to 10 millihenries. Then, okay, the other parameters are not the rated parameters. Okay, so just at a particular. So we have start point. The speed is 1,000 revolution per minute. The mechanical output power is 8 kilowatts. Okay. Then we have the peak current. Now we are supposed to determine the duty cycle. We know, so assuming current is continuous, or amateur current is continuous, then if that is, then VA should be towards this DC. Okay, we don't know VA now, we need to determine VA. We know A is equal to IA, RA here to the steady state. So plus what, EB. We can easily find EB because we know the speed at that point, right? We know AM. So EB should be equal to what? KM, which 2 volts second per rad, times your speed, which is what? 1,000 RPM, so 2 pi or 60. What is this? So then, what is EB? Okay, so that's 200.4444 volts. So then, if that's the case, then our VA, okay, no IA. Now let's draw something. The question says what? So let me draw. So this is a supply. This is our single phase converter, and this is our motor. Okay, and we don't know the VA here that we are going to find, but we know the EB over here. Okay, then what do we know again? Okay, we know output power over here. So the output power, that's the output power of, it says the speed of the output power of these two. Okay. And remember the output power is EBIA. Remember that EBIA is equal to C omega R. So this is the output mechanical power. So then EBA should be equal to what? 8.3K or 8.4K. Okay, then our I should be equal to 8.3 divided by what? Which is 209.44. So what is IA? If you have any question, put it in the chat. Okay, so that will be 40.11 amps. Okay, if that's the case, then our VA should be equal to 40.11 times 0.2 plus 209.44. Okay, what would that give us? Okay, so that will be 217.42 volts. Okay, okay, so if this is the case, we know this VA should be equal to delta the DC cycle times was VDC. We know VDC. So then should be equal to VA, which is 17.42, divided by VDC, which is 400. So what are we getting? Okay, so this was 0.54 55. Okay, in percentage, this will be equal to 54.6%. Okay, who doesn't understand what we've done so far? If you don't understand what we've done so far, voice it out.
Please, can
Okay,
you briefly go over from the beginning? Very brief.
beginning of everything,
No, beginning of this question, yeah.
beginning of this question. So what's your question?
Yeah,
What
just
don't
the
you
question.
understand about what you've done so that I explain that?
Oh, I just wanted to briefly go over.
Okay, it's not really on our part.
Thank you. Fine, you can continue.
Okay, so you believe you're convinced by this equation. V is equal to delta
Yes,
VDC. Okay, it means once we get VA, we
yes.
can get a duty cycle because this is given to us as sin. So every problem we went through over here up to this point is just to determine what V. We know that it has speed and we have
But
the
you said
mass
that the
constant.
400 is the VDC.
You said,
You said 400 is VDC, not VA.
yeah, it's VD because that's what was support the power converter.
Okay, okay.
Okay, so then if we have the machine constants and we have the speed of the machine, we can get the back EMF. Or yeah, the back EMF. If we get the back
Okay.
EMF, we know current. The product of the current and the distance is summed that to the back EMF. That should give you what your amateur voltage. Then we went through the
Yeah.
to find what back EMF. But this current was given to us. But we've been given for the output of the motor. The output of the motor is it's given by is the product of the back EMF, the amateur current. So then we know that value, found the amateur current from it. Then we just substitute everything into this equation over here. And that gave 217.42 volts. Then we know this, we can find this 54.36. I hope okay.
Thank you. Yeah, it is.
Oh,
Thank you very much.
okay. The next question, getting this. Yes. The question says that you are supposed to the approximate switch frequency. You are to ignore the resistance of the armature. Okay. So that if it is two phase, if it is a quadrant, sorry. So the quadrant also matters. If it is a single quadrant, we are assuming that the current is also continuous. Then the current waveform looks like this. This and this as well. Okay. So then it looks like something like this. Okay. So this is what the diagram looks like. Your source, then your motor over here. Then you have a diode connected across, right? Then you have a switch over here, a switch Q. Then you have your supply Q. Okay. So hey, slightly sorry. So your supply of VDC, that is what is applied to this power converter. So that if this is plus, this is minus, this becomes what? This place becomes plus, then this becomes reverse bias. So the current that will flowing through this, okay, the current that will be flowing through this over here is just going to go through this. So looking at when this switch is closed, So if the switch is closed, you go this. Okay. So this is the half where the switch is, this one is conducting, Q is conducting. And if um, Q opens, if the switch opens, initially this was plus, this minus. The polarity, you remember, this thing here is more like an inductor than a resistor. So the reactance here stores in a form of what? Current. So the moment Q go off, the energy stored here be what? Dissipated. So the remains. So it becomes plus and it becomes what? Minus. Then if this becomes minus, this becomes, and this one is for 4 bias. Current to start flowing in here. Okay. Are supposed to determine the switching frequency of this device over here. And if we are able to get the switching period, then we can find the inverse of the switching period, the what? The switching frequency. I hope that's okay up to this point. So let's look at when this switch is conducting. When it is conducting, this place is like an open circuit. The diode part is like a circuit because the diode, okay, inverse bias, it blocking. Then what are we going to see? We are going to have the equation VDC should be equal, because if the current is flowing through this and this machine is running, it's going to what? Produce back EMF EB. Okay. The motor has what? Resistance RA is a, and also has what? Indance. So looking at when the switch was conducting, so we are just looking at some transient, this one, we are doing some transient analysis. Okay, so we are looking at this switch is what? Conducting. And if this switch is conducting, the supply DC should be equal to what? RA, drop across this resistance. Then the drop across this inductor, which is what? LA, DIA, or change in IA, then what? Change in T. And the change in T, we are looking at this cycle. Okay. So this place is what? T on. And we know T on is equal to what? Delta T. Okay. So we are looking at analysis here. We are looking at what is happening here. Is that okay? So then the change in current is going to be from this point to this point, which we know as what? The peak to peak current. So that's change in IA. So it's going to be change in IA divided by change in time. Change in time will be from here to here. And that change in time is delta T. So this place will give you a delta T. Okay. Then plus what? EB. Sorry, let me write it there. So then we have VDC equal to IA RA plus EB plus LA change in IA, then with respect to change in time. I hope this makes sense. But if you check that question said we should ignore the effect of the resistance. So then this drop goes to 0. So then we just have what? VDC equal to EB plus LA change in IA, then what? This. I hope this makes sense. Okay. Then what can we do here? We know this value over here, right? We know this. Do we know the back EMF? Let me see. The approximate switching frequency. Okay. So then we can say that what? VDC minus EB should be equal to LA change in IA. What? This. Please, I hope you are following now up to this point. Okay, we know our back EMF. This is just a continuation of what? The first question we solved. So then our delta, okay, this will give us what? 400 minus 200 and what did we get for the first one? 209 point, was it 44? 209.44 should be equal to what? We've been given this, which is what? LA. That is what? 10 millihenries. 10 millihenries, right? Yeah, so 10 times 10 to the power negative 3. Then times, which is the peak to peak current, divided by what? This. Okay, sure. So what will be the difference? So, okay, then this should give us all of it divided by what? This 10 times this will give us 0.1. So this divided by 0.1, then that will cancel this and cancel this. So then we have 1 divided by this should be equal to what? 400 minus 209.44. What should that give us? 400 minus 209.44. Okay, divided by 0.1. So that will give us 1905.6. Okay, if we find the inverse of each side, this will give us what? 1 divided by this, sorry. Okay, that will give us 5 point, okay, 5.2477 times 10 to the power negative 4 seconds. Okay, so then this is going to be what? Our T on. Is that right? So if this our T on, what was our duty cycle? So divide this by the duty cycle and let's see. So that we get T. Okay, so if you divide this by the duty cycle, T will be equal to 9.646646 times 10 to the power negative 4 seconds. So if you know the period, the switching period, then you can easily determine what the frequency. So the frequency will just be the inverse of this. So 1 divided by T, and this should give you what? 1036.07 hertz. Okay. Yeah, so that is for that question. Any confusion? No. Let's move on. So what's the next question? The next question says we should find the power lost in the resistance. Okay. So we know VA uh, VA equal to IA RA plus AB, right? And if you get IA here, you get this squared, RA, then this squared. So this is the output of the motor, this is the input of the motor, this is the losses in the motor. So if that's the case, then the P loss in this motor is going to be what? The square of the current. I think we had, what did we get for the current? When we're solving the first part, 40.1. So it's going to be 40.1 squared times the resistance, which is was 0.2. So then this will give you what do you get for this? 321.6 watts. Okay. Yeah, so that's for this question. Any question? If you have any question, put it in the chat. It looks like we are going slowly. No question. Okay. Looks like no one has a question. So we can go to the next.
Someone has a question.
Okay, the person can ask. The 40.1 is the current we calculated in the first question. You remember? That's the current we calculated. That's what we used to find the VA in the first question before. Yeah, that was the when we were finding this, the current we got. Let me show it here. It should be here. Yeah, we got the current over here. I hope you can see it. Okay. So the next question. That's the last question on the DC to DC choppers. Okay, I think you have the solutions in the slide, so you can go through after. Yeah. Okay, the second one is a tram is driven by 1,500 RPM motor.
The person was asking where the 40.1 was from.
Please, I can't hear you. If your network is not good, please type it in the chat. Okay, so whilst we wait for that question, let me be reading this question. It says a tram is driven by 1,500 RPM, 600 volts series connected DC motor with a related. Okay, so you know the difference um, between the uh, series and the shunt motors. Okay, for the shunt one, the field is connected across the motor. Okay, but for the series one, the field is what in series with what the armature circuit. Okay, so then the resistance of the resist the resistance of the entire circuit will be the resistance of the field plus the resistance of what the armature. Okay, that's why it says here that the DC motor with a rated full load current of what 200 amps, the combined field and armature resistance because they are in series is given as what 0.1 ohms. The supply voltage is what 700 volts, so that's your VDC. The 600 volts over there is the rated current of what the motor. The chopper frequency varies between 50 Hz and 1600 watt hertz, but the on time remains what constant. I hope you get it. The on time remains what constant. That's duty cycle times or the period. It remains what constant. First one, calculate the chopper switching frequency and the supply current drawn when the motor is what at standstill. So the moment you see a standstill, like something should come into your mind that okay, if I'm at standstill, then the back EMF is what 0. Because when we started the course, we said that okay, noting that the motor current is what limited to what 240 volts. So the rated current for this motor is 140. But we know that when the motor is starting, it draws more current than what its normal or its rated current. Okay. And we are saying that this motor can draw current at starting. Even at starting, its current shouldn't what exceed what 240. But this same standstill, we are going to get standstill as when the motor is starting. Because when the motor is starting, the rotor is not moving. Is that okay? Then the second one says that the chopper switching frequency and the supply current drawn at the rated output. Is there a third question? I think there should be a third question. Yeah, yeah. This question is gargantuan sumo. Yeah, yeah. Okay, so this one there, it's not that difficult. So let's go. Okay, so let's write our parameters. Our RA is equal to okay, our RA is equal to 0.1. Then our I rated is 200 amps. So I rated is equal to 200 amps, right? Then our rated speed is equal to 1500 RPM. Then our VA rated is equal to 600 volts. Our VDC is equal to 700 volts, right? Then what again? What again? What again? Okay. Then it says what? The switching time remains constant. So our delta T is equal to what? 600 microseconds. Okay. This equation there, we write is VA is equal to EB. We are still doing steady state analysis here. So EB plus what? IA RA. Okay. So what are we supposed to find? The chopper um, switching frequency, which is that means we need to find this T. If we find this T, we'll find the inverse of this T. That will give you what? That will give us our switching frequency. Is that okay? But in order to do that, we don't know this value here. We know this times this, but we don't know this. So we find this. If we find the duty cycle, we divide this by the duty cycle, we get T. And we find the inverse of T, we get F. But the question says what? This is at a standstill. Then if this is a standstill, because EB is equal to Km omega R, EB will be what? Zero, because we are standstill, and standstill speed is equal to zero. So EB is equal to zero. Then VA should be equal to what? IARA. And this same value should be equal to a delta VDC. We know VDC, right? So then we know IA. Remember, it's a standstill. And a standstill, when we started, I will draw this for the last time. Okay. But when we started, I said if this is VA supplied here at standstill, EB is what? EB is zero. Then if EB is zero, then and you have a resistance here. If EB is zero, the potential across this resistor is going to be what? VA, because this place is what? Zero. Then if this place is zero, then a very high current, the highest current is going to flow in this case. Is that okay? So that highest current in this case is the limit, which is 240. So then I is what? 240 times what? Your resistance. The resistance is what? 0.1. This should be equal to what? Delta times what? 700. Okay. This will give us what? 24 divided by 700. And that will be what? Delta. So then delta, this will be the duty cycle will be 0.0343. Okay, that's like 3.4%. So that's the duty cycle. Now that we know the duty cycle, we can find what the period. The period will be what 600 microseconds divided by what 0.0343. Or we can say the frequency is equal to 0.0343 divided by what 600 microseconds. So this will give us the frequency straight away. Okay. So this should give you a 57.1 hertz. Okay. Remember, this here is micro, so okay, let me write it well. So 10 to the power minus 6, right? So it's 0.0343 divided by 600 times 10 to the power minus 6 because it's micro. Okay, so that's the period. So that's for the first question. The second question says that That's for the second question. Okay, so the first question is two in one. It says that what is the switching frequency and the supply current? Supply current. We know the supply voltage, but we don't know the supply current. So this is your power converter, right? Now we've determined what? We've determined VA because VA is what? VA is RA. So our VA is what? 24 volts. 24 volts. And with a current of 240 amperes. Okay. Then each input is what? The input voltage is 700. But we don't know the current, so I'm going to call it what? I in. Then we are going to make an assumption. You said that what? Assuming, because we will not be given the efficiency of what? The power converter. So assuming the power converter, so the PC is what? 100% efficient. If that's the case, then P in should be equal to what? P out. So then 700 times I in should be equal to 24 times 2400. So then our input current should be equal to 24 times 2400. Is it 240 or 2000? Okay, 240. Hey, so 240 all divided by what? 700. So then I in will be equal to what? 8.23 8.23 amperes. Okay, any questions so far? If you have a question, like if I'm talking and you have a question, like if it's very urgent, you can stop me and ask. If it's something I can answer after, like after I pause, you can put it in the chat. So we are okay. I can see there's no question in the chat. Good, that's good news. Okay, so that's for question A. Let's go to the B. The chopper switching. We are supposed to find the chopper switching frequency again and the supply current drawn at rated output. Okay, so now the motor is not at standstill. The motor is running. Okay, so so at rated output. Okay, so now the motor is running and the motor is running at what? 1500 RPM. So if the motor is running at 1500 RPM, it means you supply what 600 volts to what the armature. Because that's the only time that you have what this 1500 RPM speed. Okay, so that means VA in this case VA is equal to what 600 volts. I hope that makes sense. So if this is VA is equal to 600 volts, okay, we know this VA is equal to what this VDC. So that means the switching frequency, the duty cycle will be equal to what this VA, which is 600, divided by what 700, and that will give us what do we get for that? Okay, 0.857. Okay, so that means if you want this motor with this power converter, with this supply, the supply voltage, you need to operate this with a duty cycle of 0.857 in order to get your motor to operate at what rated speed. Okay, then if we have this, remember we said that what the on time is constant. So if the on time is constant, we have this value, then our t will be equal to 600 microseconds divided by our 0.857, and then our frequency should be equal to 0.857 divided by 600 times 10 to the power negative 6, and that should give you 1428.33 hertz. The units are very important. Then what will be the current in this case? So we are drawing we draw our converter here. Here the output voltage is what? VA is what 600, and the current flowing in this case will be what the rated current is because it said what at a rated output. So now the current flowing here is what 200, and our voltage here is still what 700, but we don't know the input. So I hope you know the trick. So I in assuming 100% efficient converter, I in will be what 600 times 200 divided by 700. So the input current should be what 171.43 ohms. Okay, so that's for this question. Any other question? No, we move. Oh, life is so nice. All right. Okay. The next question, which is a question three, it's also a single quadrant chopper. It says a single quadrant chopper fits a DC machine with an armature inductance of about 5 millihenries and a continuous, and a machine constant, that's km, of 2.5 voltseconds per rad. The armature resistance may be assumed negligible, so that means Ra is 0. The chopper is fed from a 400 volt DC supply, that's our VDC, with a switching frequency of what? 1 kilohertz. So remember, we said in our choppers, the switching frequency, hence the switching period, is constant. We just change what the switching time. Stating any assumption state, determine the speed of the machine if the duty cycle is what? 50% and the torque is what? And the torque is 100 Newton meters. Okay, let's go. Okay, so this is being recorded, so I'm sure by the end of today or tomorrow it will be uploaded to YouTube. Okay, so for our motor, we know our LA is equal to 5 millihenries. KM is 2.5 voltseconds per rad. The armature resistance is negligible. The chopper is fed, so VDC equal to 400 volts. And our switching frequency F is 1 kilohertz. 1 kHz. That means our switching period is what? 1 millisecond. Okay. Determine the speed of the machine if the duty cycle is 50%. So for the first one, this is equal to 0.5. That, and because you're operating at 100 Newton meters torque, then our IA should be equal to what? T divided by km. Then this T will be what? 100. Our km is what? 2.5. Then what do we get for that? Do we even need this current to do our calculation? Let me punch it. So 100 divided by 2.5. So that's 40 amps. So 40 amps. Okay. What are we supposed to find? We are supposed to find the speed of the machine. So we need EB. Okay. We know VA is equal to delta this times VDC. And this should be equal to what? Okay, RA is negligible. So plus, we are looking at steady state operation. So that's the assumption we are making. So stating any assumptions made. So our assumption is that it's steady state. Then then this place what EB. So if this is negligible, right, then this times VDC should be equal to EB. So therefore EB should be equal to 0.5 times 400, and that should be equal to 200 volts. I hope that makes sense. Then if we have EB, this EB should be equal to what? Km omega R. This should be equal to 2.5 times omega R. So then omega R should be equal to 200 divided by 2.5. And that will give us the speed in what? Rad per second. This times 60 on 2 pi. That will give us the speed in what? RPM. So I'm punching 200 times 60 divided by 2.5 times 2 pi. That will give me 963, 763, 763.94 RPM. Okay, yeah, so that's for the first one. Then the second question says the torque is now reduced to 20 Newton meters. And the duty cycle is what? Maintained at 50%. Verify that the armature current is discontinuous. And calculate the new motor speed. So the first one, we assume the current was discontinuous. And we used, first one, we assume that the current was continuous. So remember this one I drew earlier. Okay, something like this. Where from here to here is what? You're changing what? IA. Okay. So maybe its lowest value is some A, its maximum value is some B. Remember this from power electronics. Okay. Then from here to here is your delta T. Then this from here to here should be your T minus what? This. Okay. If discontinuity happens, it means there'll be a time where the switch is not conducting, the diode is not conducting. So then you have this. There will be a time where current is not flowing before the next period begins. Okay. So then there's discontinuity. And we are supposed to verify that if there's discontinuity at this top with this same what? So at the top of 20 newtons. So that of what armature current? So the armature current to be equal to 20 divided by what? 2.5. Yeah, it's 2.5. And they give us what? 8 amps. Okay, so at this current, and this is also still was 0.5. Okay, there are two ways we can do this. Let me refer you. First one is we are going to find EB divided by VDC. If this is greater than our duty cycle, then this is what? Then this is discontinuous. Okay, this is the first one. The second one, which is if you have the slide, the method that was used to find the discontinuity is using time. This one is some we proved earlier in the slide. I will show it to you. Okay. Then the second one is to see if your T off is less than T minus what on. It is from this relation that this. Okay. what does this mean? You see, actually, if we are not in discontinuity, or if we are at threshold, or if we are in discontinuity, if you add the on time to the off time, it should be equal to what T. So, or if the time that the switch is conducting, the time that this is when the diode is conducting, this is when it is conducting. So if you add the time that the switch is conducting and the time that the diode is conducting, these two times should add up to what? Your period. So it makes sense for us to say if I add the time that the switch is conducting, okay, to the time that the diode is conducting, if this time is less than the period, then means there was a point in time where none of them were conducting, because this here means what? T off plus what? T on is what? Is less than T. Is that okay? I mean, there's a time here when the wasn't conducting, neither was what the diode point. So there are two ways, but I think that this one is easier. But if you want, we can use the two methods. Strive that. But I'm going to do the easier. Okay, let me show you where this relation in the slide. So when you are reading the matters, open your eyes, guys. Okay. So where is it? Where is it? Quadrant one. Okay. Okay. So yes. So if EB divided by EC is greater than the duty step, then we have what discontinuous current. Okay, and it comes from what this relation. The T off is what we represent here as what T2. Okay, yeah. So that's where that relation came from. I'm going to use that if we are done with that and we still feel like and we have time to use the time approach, we can do that. Okay, we know. So first of all, we are going to assume that the current is actually discontinuous. And we try to prove that right. If we prove that right and it doesn't work, okay, then we know that what it's continuous. So if current is continuous, then the average current amateur is given as for the square of the duty cycle times the period times the supply divided by 2 times what this times what VD over what EB minus what 1. Okay, so we know all these parameters except EB. So we are going to find EB, then we let EB with what VDC. Find that ratio. If that ratio is greater what? If that ratio is greater than our duty cycle, then we can say that the current is discontinuous. Okay. So my average amateur current times 2 times this, all divided by this times T VD, right? Should be equal to VDC on EB minus 1. I hope that makes sense. Okay, we know this here is what 1 milli. So we found this current. Remember, we found this current to be what? Because 20 newtons, 20 newton may corresponds with what 8 amps. So then 8 times 2, and this is 5 millihenries. So 5 times 10 to the power negative 3, all divided by 0.5 squared times 1 times 10 to the power negative 3. That's milliseconds. Then VDC is 100. I think this should equal to VDC over EB minus 1. Okay, this here should give you what? I think this will cancel this. What did this give you? Let me check. So 8 times 2 times 5 divided by 0.5 squared times 400 is 0.8. So then 0.8 plus 1. If I bring this one, should be equal to VDC divided by EB. So that this will give you 1.8. Okay, then what will be E by VDC? EB over VDC is going to give me what? 1 divided by 1.8. The inverse of 0.8, 1 divided by 0.8 will give me 0.556. And you can see that this is greater than what? 0.5. Then if this is the case, then current is what? Discontinuous. Current is what? Discontinuous. And what will be the E in this case? The EB in this case is going to be of T, which is what? So EB will be equal to VDC, which is red, divided by what? 1.8. So what EB? EB will be 220.22 volts. That will be EB. Okay. Then if that is, we will be given the machine constant. So the machine constant can find the speed. Omega R will be what? 2.22. Omega R will be equal to 222 divided by what? 2.5. This will give me the speed in what? Per second, right? Then times what? 60 on board 2 pi. That will give me the speed in what? RPM. Okay, so what's that value? That's 848. 848.82 RPM. Okay, yeah. So that's how you solve the second one. Okay, let's go to the third one, the last question, and the choppers. Any question? Okay, so no questions so far. Okay, since we are doing a good job, that's right. Okay, the next question says, what should be, the next question is, the condition II. Now we've seen that there's disunity. In that condition, determine the cycle required to bring the motor speed to the value calculated in what? I. Okay. Remember in I, the motor speed was what? What was the motor speed in I? Yeah, the motor speed was 394. Now in this possibility, so that what? The motor speed is now 48.4. Okay. And this is as a result of the increment of from what? 200 to 220.22 without changing what? Without changing the duty cycle. Okay, this happens change the duty cycle, but we found a way of making back EMF for 222.22, and that has an increase what? Speed. Okay, so what we actually did was we didn't change our duty cycle of the loading. So when we reduce the loading on the top, remember you sacrifice analogy we printed from the beginning, which is actually true. What a motor actually does it sacrifices its speed to get what? To get torque. Okay, first from I said I won't draw this thing again, I'm drawing it again. Okay, so VA. So we said that was VA equal to IA RA plus what? We said that for ED was equal to what? K omega R. When the motor starts to react loading, it increases to a very high speed. Okay. It increases to a very high speed until the point where that's when it's on the point where EB is equal to V, the current starts flowing. Okay, so that will be the maximum speed. Then the moment you begin loading, the, the speed will reduce. When the speed reduces, your back EMF will reduce. Back EMF reduces. There will be a potential difference between this and this at this point. That will cause current to flow. And that current is what the machine constant is what is going to give you the torque that will load. Is that okay? So in this case, this is the machine price AC. So it means if the load come down again, potential difference, more current, more torque. You get it. If the machine is sacrificed what to get torque, then you can also sacrifice torque to get what speed, which is something that is in field weekly. You reduce torque to gain speed. Okay. So in our case right now, we've not changed our armature voltage. We maintain this constant and just reduce what the torque from what 100 Newton meters towards 100 Newton meters to 20 Newton meters. So if that's the case, it means we are increasing what EB, because what we've actually done is what reduce current. If we reduce current, what equation this has to what go up in equation what balanced. The balancing electrical, yes. So in order to that back EF increase to from what 200 to so the speed has reduced from 100 meters, speed will increase from what 200 go 100 122.22 and this has made our current so discontinuous. For the condition in II, determine the duty cycle. So now we have to change the duty cycle. So now we will change the duty cycle such that our back EMF, our ED, will go back to 200. If we go back to the 200, it has gone back to the initial in I. That makes sense. Because the only thing that changed the speed as far as is change was the back EMF. So we want to have EB to be what 200. That to have what origin. We need to do that. Now the value of this because our current is continuous at the time we make this decision. So we still have d squared times t times VDC, right? Divided by 2LA times VDC on E minus 1. So let's go to another. So this should be equal to, we are looking for a new this, and this is what and 1 milli, okay, 1 millisecond, so 10 to the negative 3. VDC is what 400 divided by 2 times 5 times 10 negative 3. The VDC is 400. Because we want to go back to initial speed, the initial will give us the back EMF of 400. Okay, minus 1. Then this value is 8. We still want to have 20 Newton meter torque. So then this will give us 8 is equal to this squared. This bad boy will go with this bad boy. Then this will be divided by this will give us what 10, so 40. Then this one will give us a 1. So then this should be equal to square root of 8 divided by 40. And this will give us a calculator root of 8 on 40. So that should give us 0.444 72. Okay, yeah. So this is what is this will be um um this is okay. Yeah, so that's that. Okay, so now we come back to we can go back to this we can continue. Okay, okay. So for the rectifiers, we need to explain this. No, you already know these things. Okay, okay. What's the intensity? Yes, let's go. So you know what, right? This is a single phase rectifier. Okay, you know, we look DC DC. Okay, now we are looking at we have DC motor. So we are looking at when we have so our motor is DC. Okay, DC motor and apply is what um our supply is AC. Okay, we need a bad boy over here that will give us certain voltage that we still want to control speed. That's the idea behind all the controllers we are using in this case. In this case, we want rectification much as we want what control over the speed. So we are going to give AC to this guy. This guy is not only just going to rectify it, it's also going to give us what our desired output DC voltage. Okay, single phase. This is what we are all familiar with. This 1 year ago we were here. Okay, so this is how it works. It's oscillating. So when A is positive with respect to N, then this is going to reverse bias, and this will be forward bias. So then current is going to go this way because this is flowing. This place positive. This will be what reverse bias. So it will go. Then it will go through the motor. I guess there's no path to ground here. So go through this, then come back to where it came from. Okay. Then if the polarity change becomes negative, we can becomes positive with T1 and T2 are going to conduct. If this becomes negative, it becomes if this positive, this one becomes negative. You have a negative here, which will come here. So this place is negative, and this is now positive, right? So negative here, and you have positive over here. So this positive is going to what? Reverse bias this, and let me use another color. Okay. So then, if the change, this one will become what? Positive will become negative. So that one, right, it will reverse bias and forward bias is trying to still go in this direction. Okay. Then it will this. Okay. So that means T1 and T2 conduct, T4 and T3 will conduct, and at times current will still be in order direction. But here, if you take just a single uh, rectifier, okay, if you take a single one like this one, you have the voltage, but you can't reverse the current because you can see the current is always what in the direction. Okay, but reverse the voltage by choosing the firing angle what greater than 90. Okay, that's, you can reverse what you can reverse what the torque. I know you understand firing. Firing angle is just the difference in angle between when a diode in this position have started conducting and when the diode starts conducting. If that's good about it. Because if you know the work, okay, okay, forward bias a diode starts conducting, thyristor will that way. So thyristor operate in three poles. We have when they are when they are forward bias, and when they are forward bias, they operate in two modes. We have forward blocking and we have forward conducting. Forward conducting. So if forward bias is that you can connect for positive voltage across it, then going to forward blocking mode. It is forwarded, but it is not what conducting. If it's conducting, you have to apply force towards the gate. Okay, so traces are turned on by what a gate pulse signal. Is that okay? Then, but if it's by turn off, turn on. Yes, you can turn them on the gate, but you can turn the gate. Make sure that the current flowing through it will goes to zero. I hope it makes sense. So, when we forward bias this diode, because we have to for a certain signal to the gate in order to have it conducting, we can wait for a certain angle or a certain time which is in the form of angle. We wait for that time or that angle before we introduce what a pulse signal to it. And after that period, so how long we wait to supply that pulse signal after it has been 4 hours is what we call what, the firing angle or the delay angle. I hope it makes sense. Thank you very much. Okay, so we are fully, so this is a fully controlled. I'm not here to take you through this. So I'm here to solve questions. Yes. So that's something small on the rectifier. So this is a single phase one. Okay, this is how the output looks like. So you can see T1 and T2 conducting over one cycle, and a diode would have started or conducting at this point. But now we are waiting for we waited from this to this before we supply the gate signal and it started conducting. From here to here, we are going to wait for this time or this angle before we supply the pulse to this one. Yes. Okay. I hope you know why we can't discuss everything. Time is not enough. Okay. Then for this one too, if for this one, if the discontinuous, your uh, your your output what your supply. Okay, the supply should be the RMS value. Okay, then cause the firing angle. If this angle is greater than 90, then you have what, this VDC equal to what, a negative value. Okay, then yeah. Before I forget, for the single phase, their distortion factor is what, 0.9, and for all of them, they are this one. Displacement factor is equal to cos of the firing angle. Therefore, the power factor is given as for distortion factor times what, uh, displacement factor. So this one, 8 power factor for the single phase, 8 power factor is given as 0.9 cos the firing angle. For the three phase, their distortion factor is given by what, 3 on what, pi, and so the displacement factor is what, cos of what, the angle. So the power factor is what, 3 on pi cos phi. Remember this. I'm not sure if I is going to provide this. This one. Okay. Yeah, so what if we want to rectify a three phase? This, you add another leg to the single phase one, and that will work for you. Maybe if we decide, if the Lisa people decide to organize tutorials after MISM, you can go through. But I'm sure at that time you have bigger worries. Yes. So the rest of it is just power electronics because there's no time. And in this case, the VDC is given by this. So it's 3 root 2 on pi times what, the line to line voltage times what cos alpha. Okay, so this VDC. Okay, I think I've already told you about this. Okay, I said that if you use a single fully controlled bridge rectifier, you can only reverse speed by what? Reversing voltage, but you can't reverse for the current. So therefore, you can't reverse torque. If you want to reverse current, then you have to connect two of them in what? Anti-parallel. You'll be fine. Yes. Okay, I think this question was solved in class yesterday. So because there's no time, the solution is also in there. You can, we have to solve it. Okay. So the assembly has decided that we skip this one. Okay. The control part. This one. Okay, let me take you through before we start solving the questions. So we want to control torque, we want to control speed. If you read the chapter one very well, okay, we mentioned in there that for controlling the torque, if you want to control torque, you have to control what? Current. Okay, then we are going to have what? A current control loop. If you want to control speed, like you control speed, okay. For the speed one, if you want to control speed, you control voltage, right? But with that one, we call it the speed control loop. Okay. Then we have the current control loop. Most of the things here, you're already familiar with them from classical control systems. So you'll be fine. Okay. So yeah, so you have the current control loop, you have the speed control loop. Then for the simple open loop control, yeah, so ideally you want a fast speed and torque what response. Like if you change your current or you change your voltage, you want that to reflect. Imagine you change a parameter and it takes like 30 minutes or it takes forever to for it to change. Like the engineer who decided thing will be a bad engineer. Okay, so you want your system to have what? Fast responses. Okay, then you want your this one to also, so for the responses, you know, you have rise time, you have settling time. You want it to settle like reach a steady state in a short period of time. You don't want it to oscillate like 5 minutes before it reaches it. Okay, it depends on other factors. Yeah, you know, engineering is always about trade-offs. If you don't want this, make sure you are ready to sacrifice something to. Yes. Then you also want what? Accurate speed holding or stable control. Okay. So even as much as you want your this one to reach its steady state within a short period of time, you want it in a manner that when it reaches its steady state, it should be able to hold that steady state until you want to change it. Not like it gets to steady state, the system is there, so that now I'm bored. I want to go back to another state. Like you get it. So you should be able to hold its steady state until you decide to what, change it. Okay. Then what happens if you employ what open loop you know, open loop control means there's no feedback. You are controlling something, you are not getting feedback. Like how do you know what you've controlled as like all the action you like how do I put it? How do you know that changing when you change a certain parameter, it has given you the result you want or not? Okay, so we all know the disadvantage of open loop control. Okay, so its advantages are they are easy to implement. Okay, but you know that speed is not automatically corrected as the machine is loaded. So the machine will not control its speed. Like you have the machine operating at a certain speed and you load it. You remember when you load it, the speed will drop. When the speed drops, the machine is not able to automatically what correct it. Okay, so then you need to know that okay, you've added some load. This the speed has reduced, so then I need to what increase it or something. Then in the open this one you don't have there's no current control. Okay, um, we are still using this relation over here. They are still using VA equal to IA RA plus this. Okay. So we want to change. You remember this relation here? It is from TE from the chapter one materials. We said that what the electromagnetic torque generated by the motor should be able to overcome the low torque. It should be able to overcome the acceleration torque. It should be able to overcome what the the windage torque. It should be able to overcome what the friction what torque. This is T. The friction torque. Okay. But here we are just assuming that what windage the windage torque is what zero. Okay. Yes. So then TE will now be equal to what TL plus what acceleration from Newton's second law of motion. You know that force is equal to what mass times what acceleration. In angular, this one is what inertia times what change in angular speed over what change in what time. Change in angular speed over change in time is what angular acceleration. Okay, that's multiplied by the inertia to give you what the acceleration torque. Just like force times mass times acceleration gives you what force. Okay, then the friction torque is what is proportional to friction is proportional to speed, right? Okay, yeah. So this time is what omega what r. Then for these two equations, if we decide to convert them to the frequency domain, if we want to convert them to the frequency domain, we are going to have VA equal to IARA plus EB, then plus DIA dt. Okay. So then to the frequency domain, this will be VA of S, IA of S. The resistance is a constant which doesn't depend on our frequency, plus EB of S plus what? LA. Differentiation in what? Laplace is what? S. Then you have what? IA of what? S. Remember, we said if we want to control torque, we control current. Let's make the current the subject here. So we have VA of S minus EB of S. EB of S should be equal to IA of S. Hey, there should be an RA here. Then this multiplying what? RA plus what? SLA. So then VA of S minus EB of S all divided by RA of S. Hey, sorry. RA plus SLA should be equal to what? Current. So it means if I have a system that has this transfer function, which is I 1 on RA plus what SLA, and I pass the difference between the potential difference between the supply and the back EMF through it, it will give me a certain current. Is that okay? So if this is my input and I pass it through this transfer function, it should be able to give me a certain current or IA of S. I hope this makes sense. Okay. Now let's look at the talk. So okay, let's go. Okay, so this is going to be the electrical kind of the electrical properties of the motor. You know, the motor is an electromechanical energy
More
converter.
resources for Ubuntu compared to Windows. And this is something you'll see with all the other softwares as well. Because most people are using Ubuntu, most answers and resources will be available for Ubuntu. Again, it doesn't
My device is connected to something.
require a lot of time. If you spend a week or so, you will start to become familiar with it. With that, the tool I want to talk about is command line. Get familiar with using command line. Again, this is something you don't necessarily need weeks to learn. Spend a
Okay.
day or week and you can
Uh,
easily
It's
start
not what is
using
for
command
Ubuntu
line.
then.
The reason I say this is when you're working with your
Then my
projects
design is
and you're
connected to
trying
some.
to debug code, you don't always look into an editor. If you're
Okay.
connected to a robot,
So
it's more likely that you just
okay,
have a
so now
terminal
let's look at the
to
mechanical
access the code
properties
and debug it.
of
So
the
learn how to
machine.
use command
So we said that T is equal to TL plus J. Here we got dt plus B omega R.
line to move files, copy files, and even edit your code. Learn some command line editors such as VI or Vim so that you can easily debug your code when you're connected to a robot and don't have access to an editor. An interesting question I received is the following. I think it would be useful to talk about how to easily acquire new
Okay,
skills in
so
the field of
this is a
robotics. I'm a
relation.
student in this field myself, and I think it's hard sometimes to
Okay,
start
please give me a
acquiring a
minute.
new skill in programming or design, for example, due to lack of documentation, lack of explanation, not too many examples, etc. I agree with the last
Okay,
statement. There
please
isn't a lot
give
of
us a minute. Our
documentation or
touchpad is
example
failing.
when it comes to robotics. Now,
Okay,
one,
we
robotics
are
is
back
a
into
growing
business.
field, and second,
Okay, so
documentation
T
is
of
kind of
S
that task that you
is
need to
equal
do,
to
but nobody
TL of
really does
S
it because it's boring. Now, if you
plus what
yourself imagine,
JS
especially as a student, you started doing your assignments
omega
maybe a
R
week
of
or
S
a day before
plus
the
what
deadline,
B
and you never really
omega
thought
R
about
of what
writing
S.
documentation. The same is kind of
Okay,
true in the industry as well.
so
You're
we
always
want
working
speed,
on
right?
lots of these
So
tasks, and
T of
documentation
S
is the last thing to be
minus
done. But
TL
before
of
you get
S
to it, either something else comes up, or because it's
should be
boring, you
equal
don't
to
really
what?
do it.
Omega R
Having
of
said
S
that, acquiring
times JS plus B. Okay, so then omega R of S should be equal to T of S minus TL of S divided by JS plus B. Okay, yeah,
skills
so
in
take note
robotics
of
is not
this and the
necessarily
one
easy, and you
we
have to
proved
get
on
your
the
hands dirty. Now, if you look at some of the
initial
interviews that
or
I've
the
conducted, time and
previous
again,
slide.
everyone gives the same
Okay.
advice. Get your hands dirty and do a robotics project. That's
Okay,
the
so
best way to learn
these are
and
going to be the
acquire new
models
skills
of
in
what
robotics. The thing is,
the
robotics
machine.
is not
We have the
something where
electrical
you
model
pick
and
an
we have the
algorithm and
mechanical
apply it
model.
and hope for it to
Okay,
work. You really have
so
to
then we
understand
have
and
the
tweak it for
this is
it
the
to
open
work
loop
with your
response.
particular set of
Please,
environment and
what you
so
see
on. So
over
for
here is
example, take the
not a
line
feedback.
following
This is an
robotics.
inherent
The
feedback.
algorithm in itself is very
Okay,
simple, but
so
if you
the
don't
machine
have to
has
use
an
it, it
inherent
might not
feedback.
work for you. For example, the
So
color
these
of
are
your
so we are saying that
particular
okay,
line
if
follower
we give it a
matches
certain
the
reference
ambient light,
voltage,
that is
which
the
is
light
VA,
around you,
which are
might be
our constant
causing
voltage.
the light reflected
So
by the line
the
to
voltage we
differ,
can
and
change,
your sensor
like
might not
what is
detect that
supplied to
light.
that
So you might
matcher.
have to tweak those
Okay,
things for the line to be
then
detected.
it's going
All
to
of this
check
to
what
say
is the
is it
speed.
takes time, and you
What is
have
the
to get
speed
your
of
hands
what
dirty to
the
really
shaft?
learn the skills. Giving a personal example, it definitely took me a lot of time to get started with the basics. Even coding, it wasn't that easy, and it took me a while before I got good at it. So make sure to give yourself that time and invest in learning those skills. Apart from projects, another useful avenue is robotics competitions. The reason I say robotic competitions is because the goal is already decided and there are concrete deadlines which make sure that you continue working on your project and not get demotivated. Plus,
Yes,
working
so
as a
we
team,
have
you
this.
can
So
help
it's going to
one
measure the
another and
speed
also get
of
help
the
from
shaft.
seniors or the community
Then that speed
supporting
of
the
the shaft
competition.
times a certain
Another
constant, which is
question
the
I
machine's
received was,
constant. So this is the machine's
I'd like to
constant.
request you to provide a
Remember,
specific
this
guide
times this
to
should
the
give us what
different
EB.
domains
We know
that
that
this
EB
field
is equal
entails
to what?
and if possible what is
Km
required to pursue
omega
each of
R.
these paths.
Okay.
I do
Then this
include
EB
a
will be
link in the
compared to
cards
this
or in the
VA.
description below
And
that
if
talks
there
more
is,
about the
they are
different
not
subfields
equal,
within
that means
robotics.
a certain
Additionally,
current
I've also
is going to
created a
flow.
guide with different
Is that
subfields
okay?
and a few
So
projects within it that will help
so
you
a
get
certain current is
started
going to
within those
flow, or
subfields. You can
this
download it from the
change. So this place
description
is going
below.
to be what
Before you go,
VA
if you enjoyed this video, make sure to give
minus
it a like and tell me about
EB,
it in the
VA,
comments
sorry,
below.
VA
And if you
minus
haven't
EB.
already, don't forget to
This
subscribe.
VA
Thank you
minus
for
EB is
watching,
going
and
to
I'll
go
see you in the
to
next video.
this over here. Okay. And from the equations or from the relations we just proved some few minutes ago, if that VA minus VS goes through a certain transfer function, which is RA plus what? SLA, is supposed to give you what? A certain current, IA, right? So that's why it's giving you what? IA over here. So this VA of S minus EB of S, when it goes through this transfer function, which is the mechanical model, the electrical model of the DC machine. Okay, so it is this electrical model of the DC machine. Basically, what you see here is what? Impedance, right? This is just the impedance of the machine. Okay, so if this um if this goes through, if this change in free how do we call it, if this potential difference over here goes through a certain transfer function, which is the electrical model of the machine, it's going to cause what? Current to flow. So like what we drew here. Okay, VA, and there's EB here. So if EB is equal to, remember we said that if VA is equal to EB, then no current will flow through here. It's the same thing that's happening here. Okay. Then this current will multiply a certain constant in the machine. So it's just a constant, it's the machine's constant. This Km, and this is going to give you a certain torque. Remember TE is equal to what? Km IA. Okay. Then so that's the T over. This is the torque that's generated by the motor. If we apply a certain load to the motor, that the motor is there, you come and apply a load to it. That's a disturbance. So if you introduce a certain disturbance, which is in the form of a torque, then that's going to subtract from the electromagnetic torque. And the difference is what is going to cause for speed. Oh God, knowledge is good. Yes, I hope you get it. Because if the torque the machine produces is just enough to overcome the torque, that means this machine can run this torque at a speed. I hope this makes sense. If the energy you have is just enough to carry me, it means you can carry me, but you can't move with me. You carry me and we will be standing at the same position. Is that okay? So then, in order to control speed, actually, you need a certain torque to cause what? A change in speed. I hope that makes sense. So if this torque over here is just enough, or if this torque is equal to the load torque, it means what? The load cannot be what? Accelerated. So then the load will be what? Kind of in equilibrium. There will be no change in what? Speed. But if their difference is greater than zero, then if that goes through the mechanical model of the machine, that will produce what? Um, that will produce a speed. I hope this here makes sense. And from this, you can find the G of S. Okay, if you find G of S, you can be able to come to the realization that the relative values of J, R, A, L, A, and B determine what the natural frequency and what the damping of this. Because this is going to be a second order, it's going to be a second order system. Okay, that which will be in the form S squared plus 2 omega naught times Z zeta, whatever they call it. Yeah, times S plus what? The this squared equal to 0. That would be the characteristic equation of this. Okay, so this is how the closed loop looks like. The closed loop here, you have an external transducer giving you what? Feedback. So you actually measuring what? The speed. An external system measuring the speed. So this is a speed transducer, which could be what? A taco generator. Exactly. So you have a taco generator which measures speed, right? Okay. So you have a certain reference speed, then it measures the speed based on the difference. It's going to give it to a speed controller. The speed controller is going to control the speed, and the output of the speed controller is what? A reference current. And that reference current will go through a current control loop. This is a whole control system on its own. So it's going to, that's why we said that current control loop. So this will go through the current control loop. And the output will be what? The armature current. Then that armature current times the machine constant will give you what? The electromagnetic torque. And the electromagnetic torque, we are assuming that there's no load connected. So that electromagnetic torque will go to the mechanical model of the machine and give you what? Speed. Okay. So this current loop over here is what you have over here. So that thing you see, that small box you see up there, this is how it looks like. So you can see here that its input is what? Its reference is what? The IA ref, the reference armature current, as you can see from this place. As you can see from this place. So then the current controller has what? A current controller, which is what? A PI controller, and it has what? A power converter. So what this current controller does is it takes a certain reference current. Okay, then it gets what? The current that is flowing through the armature right, and then the reference current. Then it gives you a certain error. Then that error signal is sent into what? A current controller, which is a PI controller given by this transfer function. Okay, then the output of this is what? A reference voltage. It is this reference voltage that is supplied to the power converter for the power converter to give you what? The armature supply voltage. Okay, then based on the back EMF, it's going to give you some error over here. And if this error goes through the electrical model of the machine, it gives you what? It gives you a certain current, as you can see here. So you can see the input to this is what? The IA ref, and its output is what? IA. Okay. Then you have a current transducer that measures this current and feeds what? The Okay, yeah, so that's it. So what when designing, we usually design the current controller first because electrical signals are faster than mechanical signals. Is that okay? We design this first, and when we are designing, or at least in this, the power converter was assumed to have what? To be just a proportional controller, like it just takes maybe a certain voltage, let's say 5 volts, and gives you 10 volts. It takes 2 volts and give you, let's take it 4 volts, like just a proportional. Is that okay? So just a constant. And this here was derived using the assumption that the motor is at standstill. So there all the equations down there that the motor is at standstill. So if the motor is at standstill, it means the disturbance here is zero. So EB is zero. Okay. Then if EB is zero, the current transistor here is also approximated using what? Like just a constant. Okay. Now maybe when it measures 5 amps, it reports it at maybe 25 amps or something like that. Something like that. Okay. Yes. Then if that's the case, then your forward transfer function is going to be what? This over here times what? The power converter transfer function. Let's take it KP or KPC, okay, for power converter, then times what? This. So if this is equal to zero, then this VA goes straight to what? Into this. Then this will be 1 on what? RASLA. Okay, so then you see that this here is going to give you what? This here is going to give you a second order system. Okay, it's going to give you a second order system which you can solve, and there are two ways you can solve that, because you know there is that the total transfer function is given by the open loop transfer function, or G of S divided by 1 plus G of S H of S. Why am I even writing? The thing is here, I'm still writing it. Okay, so with the approximations we made, this how your G of S will look like. So if your G of S looks this way, then your T of S, you have G of S. Then we said our H of S, we are just going to approximate it by a certain constant. And that constant in this case is what? KT. Is that okay? So then you can easily find out your T of S, which will be your overall transfer function or your closed loop transfer function. Then if you have this as your closed loop transfer function, this is your characteristic equation, which is 1 plus G of S h of s equal to 0. And this is what you use to draw your root locus. Okay, so since it's a second order system, this relation here, if you expand everything, is going to be in what, this form. Okay, the second order. So you are going to have a certain s squared plus what, a times s plus what, b. Okay, where b is not, it's not like, it's not necessary that b has to be a constant. It can be any expression. It can be any expression. So when you find your this one, if it's second order, you express it in this form. And if the our characteristic equation is going to be in this form, then we can say that okay, then this is going to follow s squared plus what, 2 omega naught mu times what, s plus what, it's a second order system, so plus what, omega naught squared. Okay, then in this case, omega naught times the damping ratio should be equal to what, a, and omega naught squared should be equal to what, the which this is our damping ratio, and this is our natural frequency. The natural frequency, whatever they call it. Yes. Okay. So in this case, from this g of s over here, remember this is a PI controller. It's a PI controller because if you expand this, you are going to get what, kc plus what, kc kc over kc plus a kc ac on what, s. So this is the proportional part, and this was the integral part, because 1 on s in what, Laplace is what, integral, right? So then you have to find this kc, and you have to find what, this ac. Okay, then ra it's known, la is known. Okay, so in solving this equation we have over here, or the system, the characteristic equation, there are two ways you can go about it. Either you use the post zero cancellation, or you use the characteristic equation. If you use the post zero cancellation, it means you are going to find a pole that will cancel what, the zero, or you find a zero that cancels the pole. Basically, that's it. Okay, because in here at the top here we have, are you guys still there? I'm just talking plenty.
Yeah, we are here.
Okay, so okay, we are doing post zero cancellation. So in here we are going to have a certain pole. If you look at the overall transfer function, we are going to have a certain pole in the there's a pole. We are going to have a certain zero in there, which is AC. So we are going to look for a pole that is going to cancel what, this one. That means the pole should be equal to what, the pole should be equal to the zero, such that they'll be on each other, and they will cancel the effect of what, each other. Okay, that's the pole zero cancellation. So, but all the questions you won't use pole zero cancellation, so don't worry. But you just have to know. So that if you are choosing a pole, if you are doing the pole zero cancellation, then this is a zero and this is a pole, they must match each other. The disadvantage in this is that the moment AC is not equal to AP, you have a problem with your system, because that's how you design it, that at all times the pole will be equal to what, that zero. So if you know the these values here may depend on other things. Okay, as we will see here, we are saying that what, this AC should be equal to AP, and for this to work, this must be equal to, I think, RA over what, LA. Okay, so where is it? Right. Laptop frozen. Where is that bad boy? Okay, yes. So that AC should be equal to AP, equal to RO. We can't translate that, because remember, distance of conductor somehow is affected the temperature. right? For insulated, as their temperature is increasing, resist drops. But for conductors, as their temperature is increasing, their resistances are increasing. So then, if you do this and this changes, okay, if for the inductance of the motor will always be that value, but the resistance can change with temperature. So if the motor heats and this one changes, that means this will no longer be equal to this, and then it okay. Then if you are able to meet this requirement that AC is equal to AP equal to RA over LA, then your power transfer function reduces this. What here is the time constant. Okay, we can prove this. There's no time. Maybe if I don't forget, I may take a picture of the proof and send it to you. If I don't forget, I hope I forget. Yes. Okay. Another way to use the characteristic equation, which I've already talked about, we said that what this one is going to have this characteristic equation. Then if characteristic equation, then we can compare it to what the general characteristics of what second order system. Then we can solve that. Okay, so that's for the first part. Something small about this bad boy. We said, remember the equation right up here, which gives us a second order system. Remember we said that our power converter can be approached as just a proportional gain, right? That's true. It's not entirely true. And if it's not entirely true, then it's going to affect our equation. Because if for the chopper, if I started a period and as soon as I started the period, I changed the duty cycle, the system would have to wait for the cycle to be completed before it starts using the new cycle during the next period. So that if I apply the change in, remember we are following the cycle to control. If I apply this at the beginning of the cycle, I will have to wait for the entire period of what? Entire period in order for this to take effect. So that means the delay is going to be, or the more delay I can have here is when I apply the change in the duty cycle for beginning of a cycle. So that the maximum delay is going to be what? T. But if I apply the change just at the end of cycle, that means once a cycle, the next cycle starts. So that means there will be a zero delay because it just have to start, like it just ended a period and it's now about to start a new period. So it took that new duty cycle and start with it. Okay. So then my average will be what? The maximum plus the minimum divided by 2 is going to give me what? T2. Is that okay? So then the power converter actually is to be a first order lag system with a constant of what? T on 2. Okay. So that means the average delay. So that means the average delay in a power converter is what? T on 2. Okay. So then we can mod this as that lag with a time constant of T on 2. So that's why then it's going to be like this. Though it has a proportional gain, but it's not just a gain. So it's a gain times what? A certain lag. That lag is 1 on 1 plus S times what on 2. So this is the time constant. The time constant is what? T on 2. Then if you look at the single, if you take a 50 hertz supply, that as we have Ghana, the period is going to be what? 20 milliseconds. Okay. Remember this is AC. The first one is what? DC. It's going to be what? it's going to be how do we call it? 20 milliseconds. Okay. But remember in AC, your output your output here is going to have what? Its frequency is going to be like twice. Its frequency is going to be twice uh, the frequency of the supply. So its is going to be 100 hertz. That means each period is going to be what? Half of what? The supply period. Okay, so that period is going to be what? 10 milliwatt second. And this because you have two pairs of thyristor conducting per watt cycle. So this is actually whatever you see over here is actually this. Okay, and in the supply this is a cycle, but in the output this is what a cycle, and this is what another cycle. Within the same what input, a single input cycle. So like this flipped to this. Okay, so the frequency is going to be two. The period is going to be half. I hope that makes sense. So then if the maximum delay is 10 milliseconds and the minimum delay is 0 milliseconds, that means the average delay is going to be 5 seconds. So then this one can also, for a single phase rectifier, it can be modeled as what? A propagating and what? A first order system, time constant 0.05 or 5 milliseconds. Okay, someone else that I go over the frequency and the period. So this is your input, right? And this is a rectifier. This is a full wave rectifier. So for the input from here to here is what? A cycle, right? From here to here is a cycle. So that means the time taken to complete this is what? A period. But in your output, this is going to be rectified. So you are going to have something like this. Something like this. Okay. And in this case, the repetition starts from here. So then this becomes what? This becomes a cycle. This becomes a cycle, right? So what is it? What's period? Period is the number of or how long it takes to complete what? How long it takes to complete one cycle. So if here it takes 5 seconds to complete a cycle, here it's going to be what? Half of what? What is happening at the input. So then this place is going to be what? 2.5 seconds. So the frequency to double here and the period is going to be what? But here you can produce what? Two two cycles within this input within what one cycle for what the input. I hope this makes sense. If not making sense, pray. Prayer can do all things. Yes. So if you have say the three-phase rectifiers, you have six thyristors what content. Okay. For 50 hertz, the period is going to be what 20 milliseconds. Okay. The maximum delay in this case, because here the fee is going to be 6 times the input frequency. Okay, if you go back and you study the waveform you are going to have something like this. It's going to be 6 times. Without 1, 2, 3, 4, 5. I've done 7. It's going to be 6 times. So that means the output frequency of the output waveform is going to be equal to what 6 times the frequency of the input form. So that means the period is going to be what uh, input period divided by what 6, and that's going to give you what 1. That will give you 20 divided by 6. 20 divided by 6 like 3.33, right? Milliseconds. Okay, that means this will be your maximum. Okay. Your minimum delay is 0. If you find the average delay, it will be 3.33 divided by 2, and that will give you 1.67 milliseconds. So that means this one is going to have what? It's with a time constant of what 1.67 seconds or 0.00167 seconds. Yeah, so that's for that. Okay, so that's for the current control loop, then you come to the speed control loop. So if you remember, I said you design the. We are taking two. Should we close? Okay, we said that we design the current control. After that, we design the speed control loop. Okay, so when you are done designing the speed control loop, you have to approximate the current control loop to maybe a first second order system, a first order system, or a constant before you design the speed controller. Okay. You the lock. Okay. Okay. Yeah. So you just have to do that. That one too is just it's just like doing the for the speed controller eight this one eight for the speed controller eight transfer function is just like the current controller KC S plus what AC divided by what divided by SK. Yo, let's solve some questions. Okay, this one will take long time. The solution is here. Anything you don't understand, you can ask. There's no time. Okay, there are some other questions over here. Okay, so this on the fully controlled rectifier. You have a 250 volt, 100 RPM DC motor connected to. So these are the ratings of the motor. Okay, it's connected to a 208 volt three phase 60 hertz line. Use what? So this is the rating of the machine, and the line to line voltage of supply is for 208. Okay, and the frequency is 60 hertz. And we are using the phase bridge converter. Okay, so that means this the line that will go into the power converter, the series power converter. And the full load armature current is for 2,500 amps, and the armature resistance for 4 millihenries. We have to calculate the firing angle under the full load conditions. Okay, we know that for I'll just solve it. So we know that our VD or our VA in this case. Right now we are doing three phase to DC. This should be equal to 3 root 2 divided by pi V line to line cos what alpha. So as we need to determine V in order to determine this, this has been given to us. Okay. So we go back to our relation. We know that VA is equal to a RA plus what EB. Right. Under rated conditions. Okay, let me read this one. Okay, so under rated condition 150 volts entering what supplied across the armature. So that means the rated condition, the output of um, the output of the power converter should be 250. Okay, so VA should be 250. So 250 is equal to 3 root 2 divided by times so 208. 208 cos what alpha. And if you multiply this over here, it will give you 280.899. So this is going to 250 is equal to 280.899 cos what alpha. So then alpha is equal to what? The cos inverse of 250 divided by 280.899. And this here should give you punch it 27 27.13 degrees. Okay, I hope that makes sense. Okay, then the one says what should be the firing angle? The firing angle required for the motor club is rated at 400 RPM. So 400 RPM means that the back EMF has what reduced, right? So then, if the back EMF has reduced, it's because we are no longer supplying what the output of this of VA is no longer 250. Okay, it means the VA is no longer 250. Then we need to find VA now. We know that VA is equal to IA RA plus what EB at steady state. I hope that makes sense. Okay, so V is equal to IA RA plus EB. Okay, but we knew 250. Um, okay, for the initial one we just solved, we knew that when 250 was up to the amateur voltage under rated condition, so you have IA RA plus EB. Okay, the initial, let's find the machine constant. So then this is going to give me a 250 should be equal to what? Rated current is what? 2500. So 2500 times what? The resistance is what? 3 milliohms. So that will be 4 times 10 to the power negative 3 plus what? EB, right? Therefore, EB should be equal to this times this should give us 10. So you subtract from this, that should give us 140, right? Yeah, 240. Okay, so when we have 240, we need a speed of 1200 RPM. So then our Km is going to be 240 divided by 1100 RPM. And this should be equal to what? What's Km? 240 divided by 120. So that was, that's pardon. Okay, so this should give us 0.2 uh, volts per watt RPM. Okay, then if that's the case, in this case, we want to find V, and we are looking at what 400 RPM. If we are looking at 400 RPM, then EB should be equal to 0.2 volts per RPM times RPM, and this should give us what 80 RPM, 80 volts. Sorry. Okay, then what will be our VA? Our VA will be equal to IA, still underrated. Yeah, underrated torque. So our current is still what 2500. So you have 2500 times what 4 milli, 4 milli plus what 80. Then our VA should be equal to what? They give us 10. So then VA should be equal to 90 volts. Now that we have VA, we can find our firing angle. So then this VA should be equal to 3 root 2 divided by pi times 208 cos what? Alpha. Okay. So then this should give 90 divided by 280.899 should be equal to cos alpha. So then alpha should go to a cos inverse of 90 divided by 280.99. Okay. So then alpha should be equal to what? What's alpha? 71.32 degrees. Okay, the next question says calculate the reactive power the converter absorbs when the motor develops full torque at 400 RPM. Okay, so we said that for the three phase, power factor is equal to 3 on pi cos what alpha. So then this will give 3 on pi cos 71.32. So this gives us 0.306 lagging. It's lagging because it's a motor. Okay, so this is our power factor, but we are supposed to find reactive load. And if you draw the power triangle, you have your apparent power here, you have your reactive power here, and you have your active power here. Is that okay? You have active power here, and you have this angle. This angle here should be what? Cos inverse, because uh, cos cos the angle here should be equal to what? Cos the power factor angle should be equal to 0.306. So then to find the angle here, we have to find what the cos inverse of, and if you find the cos inverse of this power factor, find the cos inverse of the power factor, that's going to give you an angle of 72 point 72.18. Okay, so that means the angle here is 72.18. Then I'm looking for reactive power, so Q should be equal to opposite over what? I know I can find P. Okay, so and I want to determine Q, I use tan. So this should be what? E tan 72.18. How do we find P? Right, we need to look at the output of, yeah, so the P over here, we have a certain input to the power factor, and a certain what? Output leaving. Okay, what's the input? What's the output of this? Oh, yeah, so it's so I think 100% efficient. So okay. So VA here is what? VA is 90, and our current is 2,500. So then what will be power? Our power is going to be what? Let me calculate that. 90 times 2,500. That will give us 225,000. So that means our here is going to be this voltage times the current. Okay. And then so assuming 100% efficient. So input power to output power. So then this power P here is going to be the product of this, and this is going to be 225k, right? So then Q should be equal to 125 tan what? 70.1, is it 15 or 18.18, and Q here should give you what? 69 699.95 kilowatt. But this is reactive power, so it's kVAR. Okay, so that's the end of this question, and probably that's the end of today's session. Um, there's two other questions down here, but time will not permit us to do. For one, I don't solve it. This one is just drawing. You look at it and it should make sense to you. It's the third one that I would like to solve, but we don't have time. Okay, resources are limited. Yes, so we'll end here. Thank you for attending. Those who are not here, I'm sure it will be uploaded to YouTube. You can check it out later. So thank you for your time. Bye bye.